Thank you, Jos, for inviting me and STOWA for inviting me to this meeting here. And as Jos already said, that I will concentrate a little bit on the fish here, but I will also touch the other thing because they all interact. And since I'm the first speaker, I think I have the opportunity to go a little bit around. We already heard from Jos that the temperature is changing, but what is very important, I think, from our systems and especially shallow lakes, is that the precipitation is changing and runoff. And we also saw that this in his talk here before, that this is just over 100 years we can expect in some areas here in Europe a 40% reduction in runoff. And in other areas where I am living, we can expect it's raining more and more, and it's already peeing down there, as you can see in one of the next figures. But the first one is Turkey, where you can see here how it is going now. It's not only because of global warming, it's also because of irrigation, increased irrigation, that is of course affected also by the warming. So you can see dramatic changes over very few years here. It's not easy to swim there anymore. And in Denmark it's peeing down every day, and it has been that for 100 years, as you can see. This is the long-term change in precipitation in Denmark, and it was around 620, and now it's much higher. And it's not a small percent increase, it's really dramatic increase over 100 years. And you can see, of course, the consequences, the runoff in the rivers is also changing. So you get much more water in the system, and with water you also get nutrients. And here we have some data from Danish streams, where you see nitrogen. It's the diffuse loading of nitrogen and phosphorus here, and related to runoff. And it's quite a dramatic effect you have of runoff on the loading of nutrients. Of course, if you get more water, you also get more nutrients in the water. But if I have to go back. But if we try to put it a little bit in perspective, then if we had the same agriculture 80 years ago, we have of course not had that, but then we'll have had a 33 to 40% increase in loading to the system just because of the change in precipitation. So it's really not minor thing, it's a dramatic increase in loading to the system we have had over the time. And the expectation for the future, if we use the models, global climate models on the regional level, then it is also, if you see here, it's the change in runoff up to 30% in some areas, and you have also 25% increase in nitrogen, and phosphorus can also be very high. And this is even with models that are a little bit conservative, probably it'll rain even more in the system. So we get much more nutrient into the systems over time. The other thing that happens in the lake ecosystem is that because of the temperature increase, you also get more internal loading, release of phosphorus from the sediment. And this is not because the diffusion of phosphorus from the sediment is depending on the nutrient. It's because the metabolism in the sediment goes up. You get oxygen consumption in the sediment to a higher extent, and then release of phosphorus. And you can see it here that you have the effect of temperature. It's quite a big increase you have of phosphorus release. And you can see some experiments here from Danish lakes, 7 degrees, 20, up to 21 degrees, and you can see a much dramatic increase in release of phosphorus from the sediment. So you get more nutrients into the system, and you get also more nutrient released from the mud to the water. And also because of the temperature change, you change the seasonality on the release of phosphorus. In Danish lakes, we can see that now in the wintertime, when it's cold, you accumulate phosphorus in the sediment. This is, if it's positive, it's a retention of what's coming into the system. It goes to the sediment. And in summer, because of the temperature increase, you have a release here. And then in winter, you retain it again. But when the temperature goes up in winter, you have release now in winter also, not only in summertime. So you enhance the period where you get release of phosphorus from the sediment. And you can see now, if you compare it with how it is in Florida lakes and Danish lakes, and just take the most eutrophic ones are here, where you have a retention, and this means low phosphorus concentration, then an increase in summer, and then down again. But if you look at Florida, the same type of lake system, it's all over the season that you have phosphorus, high phosphorus concentration. So you lose this capacity to hold phosphorus in the sediment in the wintertime, and therefore you have higher algae biomass. So one thing is that we can expect higher nutrient concentration because of global warming, and this will lead to more algae, of course, and suspended matter. So warming enhances eutrophication. Many have said it, but I'll say it again here. And this may be one of the consequences here. But another thing, and that's the main part of my talk, because I was asked to do that, is that there are also major changes within the system that accelerate this eutrophication. And one is that we get more bad guys. We get more zooplankton benchivorous fish. You have the bream here, and they become more important in the system with the temperature increase. And you get less of the good guys here that should control these one, and then give the water fleas here down a chance to remove the algae. So when you get more bad guys, you get less of those and more algae. And you can also end up with really bad guys. Here is one here, the carp. And this is an example from the Azores in the mid-Atlantic, where they stocked carp because the lakes should have fish, they say. And then they stocked carp, and you can see this beautiful lake here is completely filled with algae because of the carp disturb the sediment and get the nutrients to the water. And we get more and more of those in our country. You already have them in most of your system, but they will become more important in the future because they like warm, they like it hot. There's also another one that is very bad, and that is the catfish. This one can be piscivorous, but most of them are benchivorous, and they also disturb the sediment. And when you have catfish, you have a turbid water often. And this is one of the consequences. This is from Italy, for instance, a few months ago, where we do in Visor project, where we're looking at these guys here. They're filled with catfish in these systems, and at relatively low nutrient level, and they were turbid. So one of the things we see, and this is another project called EcoFrame that Brian Moss was heading some years ago, you can see that the change is going from north of Europe to the south here, going from ice, what they call ice, to warm here. Then you can see that the ratio of planktivorous fish, planktivorous benchivorous fish, it includes bream also. This ratio goes up with the temperature, and it's a logarithmic scale, so it goes really up. And the consequence of that is, this means that there are more fish to eat the zooplankton, you can say, that control the zooplankton, that should clear the water. And the consequence is also, of course, you have less zooplankton per unit of algae. Now it's given as chlorophyll A, but it's just the algae biomass in one way or another. And you can see again here, if you look at this figure here, it's going down, and again a logarithmic scale, dramatical reduction in grazing capacity of the zooplankton on the algae. And therefore the algae flourish well in these conditions. The other thing is that you get very small fish. You get a shift in structure of the fish community from relatively large one in the north to small ones. But I always say that they're still happy down there, so you can see. So this, but there are a lot of small fish, and the big ones, they are more or less gone, as you can see. And this you can even see, you can say, it's down south, and it's because of the biogeographical conditions and all these kinds of things. But then you can look at it in Swedish lakes, going from the northern part of Sweden here to the southern part of Sweden. This is perch, which are piscivorous when it's big, but when it's small, it's a bad guy, because then it eats zooplankton. So if you get smaller size of those, then you are in trouble. And you can see going from the north of Sweden here to the south, you get more and more, a higher percentage of small perch in the catch. It's the same method that has been used everywhere. So even just through Sweden, you see these changes going on. And we can see now in Denmark, with increasing temperature, you have more small fish in the system. So this is quite a dramatic change you have. And small fish means eutrophication, because that's exactly what we see when you have more and more eutrophic conditions. There's more and more phosphorus here. And you can see our guy perch here. It's becoming smaller and smaller with increasing phosphorus concentration. So it's exactly the same that happens when you shift from cold to warm conditions. You eutrophy the system also in the fish community, you can say. But they're not only becoming smaller, they also have a shorter lifespan and earlier reproduction. And small fish eat like babies. Every 3 hours they need something. So they take Daphnia. So the zooplankton has big problems under these conditions. The other thing is that they become a little bit more lazy also, these fish. Because in the north they know that you have to spawn at the right time, because the winter will come and you have to have your youngs, they have to be big and healthy at that time. But in the south you take it a little bit more less serious, because it doesn't matter, it's still warm in winter also. And you can see it on the fish community, they have learned from this, from the people also. As you can see here, this is a spawning all at the same day here. Within 5-10 days they have spawned all of them. But when you come further south, you can see there's 60 days between. It takes time. It's next to manana. And it's also clever because it's not as smart to put them all out at the same time. It's good to have them from time to time a little bit, put a little bit in there. So they take it much more easy. But it also means that the pressure on the zooplankton is there all year round, you can say, because they come at different times. And I've seen it here, even in Holland, that the roads are so small in September. We never see that in Denmark. So even just going from 800 kilometers, then you see these changes. We can also see it another way. We can try to look at the data. We have many data from Danish lakes, and the temperature has changed, as you can see here, over time. But I'll not go into detail with that. But we try to now to model this using all the data from 800 Danish lakes and try to look at Daphnia biomass, the grazers, the one we want to clear the water. And then put it in relation to phosphorus, mean depth, and water temperature. There could be other factors in. There have been, but they got out in the analysis because they were not significant. But you can see you get more Daphnia with more phosphorus because there are more food. But what you also see is that the temperature effect is enormous. This is the slope you have on this figure here. So if it's negative, the slope is not shown negative, but it is negative here. If it's negative, then means that the Daphnia biomass goes down. And if it's positive, it goes up. This is the factor you put on the regression. And you can see that this is a big effect here on temperature in summer. And it's not because Daphnia don't like high temperature. It's because young of the year fish comes in when it's warm, and therefore they control the zooplankton even more if it's high temperature. So all these small fish are coming in now when it's warm, the warm years. And then you have an effect also of depth, but that doesn't matter here. You can also see on the individual biomass of these cladosons, the larger they are, the more they can eat the larger algae. The smaller they are, they cannot. And you can see again the same reduction here in the summertime, when you have the young of the year fish. And this means when you go from the big ones that also can eat the blue-green algae if they are big enough, to the small ones, then you lose this capacity to control the blue-greens. And the blue-greens are the worst one, we know. The other thing is that ice duration is diminishing. And this has some consequence also. Because you always have fish kill on the ice. It's not good for the fish, of course, but it's good for the lakes. Because then you get rid of some of the bad guys. And also if it's a cold winter, you get rid of some of the water birds like coots that eat the macrophytes in the system. So warmer winters means that you get more of the bad guys and more coots to feed on the macrophytes, and this means less chance to have a clear water conditions in it. And you can see we took an example here from the Danish lakes. We have the last cold winter was in 95, 96. Now we have one again here. So we will see the same pattern, I think, next year. But what we see in this cold winter compared to the other one is that you have more Daphnia in the summer after. Simply because you had a lot of fish kill on the ice, so therefore a higher amount of Daphnia in this year compared to the other years nearby. So you have a higher grazing capacity, but now you're losing this. Another example here is from Canada, where we compare Danish data and Canada. Canada is cold because it's in central Canada. And the winter is 5 months, and in Denmark it's only these 14 days to 1 month if it is high. And then we try to look at the chlorophyll, the amount of algae in the water, per unit of phosphorus out here. And you can see that in the Danish lakes are up here, and the Canadian lakes are a factor of 2 lower or something like that. At the same phosphorus loading, same phosphorus concentration, you get much less algae in these systems, simply because fish die on the ice, and therefore you have more zooplankton. And how do we know that? We can compare the zooplankton-phytoplankton ratio, the indicator of grazing capacity in the system. And this is the Canadian lakes, a factor of 2.6, very high. In the Danish lakes, 10-fold lower. So the grazing capacity is 10-fold lower in the Danish lakes, just because of this. So what is happening now, if we try to sum up all these fish things, is that in a healthy Danish system, we have many of these good guys that control the bad guys. Therefore, we have not so many bad guys. We have a lot of these zooplankton, the macrozooplankton here, the big one, the eat of the algae. That's fine. But if you now have the degraded system, the eutrophic one, then you have very few of the pachyvores, a lot of these planktivores, and very few of the water fleas because they are, it's not good, this one, because they are eaten, it's here, They are eaten by the fish and therefore not control on the algae. But if you take the warmer system, then you even lose it here, you can say, in a low nutrient level, because you always have these small fish, also in the nutrient poor system. And this means that the capacity to control the algae is low, and they become very sensitive to increase in the nutrient to the system, even if you have low level. So that you change the capacity to keep the system clear. Another thing, if we take all these data with algae, then we can see that the algae composition is changing. Not only do we get more algae in the system, we change the composition quite dramatically. It's the same as I showed before, but it's the slope of this relationship. But just only look at the temperature effect. That's the blue one, the dark blue one. It's not easy here. And you can see that diatoms don't like high temperature, greens don't like high temperature, but all the blue-greens, they like very high temperatures. And also the dinophytes like very high temperature. So you have a big effect of temperature on algae themselves. In addition to this, the grazing capacity on them goes down because the fish community structure changes. And I'll just put a little movie here. You can see this is the different months. But if you take June and July, August and September, you can see the changes in cyanobacteria at a given phosphorus level and given depth is increasing quite dramatically with temperature. It's a fixed nutrient level. And if you take the next one, also the nitrogen play a role. If you believe in these models here, then you can see that a big effect of temperature here at a given nutrient level. This is nitrogen up here. Increasing nitrogen, you get more cyanobacteria, but if the temperature goes up, it escalates. So lakes become much more sensitive to enhanced nutrient loading, and this means that the critical nutrient loading for shift to a clear state decreases. What then about the submerged macrophytes? We know that they clear up the water, and I don't have to tell that in Holland because you've been working a lot with it here. And one of the reasons, there are many reasons, but one of them is number 2 here, that the zooplankton hide in the vegetation during daytime, and then they go out in the night and feed on the algae. And they can hide from the predation from the fish. And you can see it if you don't believe it, and then you can just see that here, that they're doing, they go in here, as you can see, and then they go out at night. So it's the proof of everything here. So what we see always in this system is that if we have a lot of plants in the system, and this axis here, then they are clear. And if we have no plants in the system, then they are clear if they're low nutrients. But if they're high nutrients, they're very, very turbid with a lot of algae in the water. But what happens now when you go to warmer lakes, and this is examined from Florida, from the subtropics, then you can see this capacity to clear the water goes down, that the plants are not so efficient as they were in the temperate lake. So plants don't have this capacity in the same extent in the warm lakes. Why is it so? Then Marianne Meerhof from she did a PhD in Denmark, together with some of us, did some experiments looking at the shallow lakes in Uruguay, in the subtropics, and the temperate lakes in Denmark, putting out artificial plants of different kinds, imitating real plants, as you can see up here, to get the same structure in both systems. And what did she find? She found enormous amount of fish in the vegetation. And you can see it here, this is the temperate zone, exactly the same conditions. But in the subtropics, you even have to break this one. You have 400 fish per square meter in this vegetation. And if you're a water flea, a Daphne, you will not go in there. And if you even do experiments and they can choose between plants and fish, they go to the fish nose because they are afraid of the fish because they think that fish are much more abundant in the vegetation. So they know from their mothers that it's not good to go in the vegetation. Stay away from the vegetation, they probably have said many times. And there are good reason to believe in your mother here, because you can see this is the number of fish, and you also get a lot of shrimps. I don't have time to go into detail with that, but all these invertebrates, all the invertebrates and cladosans, they disappear within the vegetation. They are abundant in the other system here, in the temperate system. So you lose the refuge capacity for zooplankton because fish like to be there. Then you can say in the future we can get much more of these blue-green algae, and you can see them if you go down also in the warm countries and the dangers and all these kind of things. But can we do something now to improve the conditions? One possibility is, of course, to do biomanipulation. And you know, from Holland here also, and Denmark, we have done a lot of them. They're not always function very well on the long term. But one thing that is interesting with these case studies with biomanipulation is to look at the composition of algae following a biomanipulation, where you remove these bad guys, get the Daphnia back, clear up the water. It happens every time you do it, but the long-term perspectives are not always good. But what you can see is, interestingly, because we want to combat these blue-green algae, the cyanophyte is not good, but it's up in the right corner. Then you can see that this is again a logarithmic scale, that you have a very big impact of biomanipulation on the blue-green especially. And if you have one at the 1, then it's there are no effect, but if you are going down, then it's maybe if 0.1 is a tenfold reduction. So you have a big impact on the short-term basis, but on the long term it's not always good, as you can see. So a strong effect on cyanophyte. So this is one possibility to meet the criteria of this Water Framework Directive. So a clear effect maybe in 6 to 10 years, but then there is not very good results, and you may have to repeat it. And you can see that this is one way to do it. But if you now come to the warm countries, then you have all these small fish. And you can see the cat is looking at some of these exotic small fish that are not exotic where they live. Can we then do anything with biomanipulation in this system? Because we'll expect that as soon as you remove the fish, a lot are coming back because the reproduction is high. And we see that also. But it seems that it is sometimes possible. And the reason is that the fish are not only affecting the zooplankton, they are also affecting the benthic resuspension, especially all these benthic fish. So it's maybe the bottom-up effect you can change by doing biomanipulation. And they have done it in China here. This is a guy called Zhengwen Liu. He did an experiment here. You can see very turbid, and now it's very clear, and you can see it's here, where he removed a lot of the fish there and added some stock with some piscivorous fish. And you can see the restored side and the disturbed side. Very big effect. So even in the subtropic, it seems to be possible, but we don't know about the long-term effect. And we didn't get, in this system, we don't get an effect on the zooplankton, because the small fish are still there. If I should conclude, then warming enhanced the risk of eutrophication, higher internal loading, higher risk of filamentous algae, I didn't show that, but on blue-green algae, higher fish predation, lower capacity of macrophyte to clear the water, and more importantly, lower nutrient threshold needed to obtain good ecological status. So we are in trouble, I think, in the future. Then we can just say, shall we do anything? Who cares? We don't believe in this global warming. It's so bloody cold this year, so why this? Or we can say that it's not my fault at all, because I'm such a little guy, so I cannot do anything. But maybe we have to do something, each of us. And one thing is that we can step down one trophic level and go away from eating all this meat here. And here you see a good example, a Dutch man that has a bad conscience now, I think, because he's eating this kind of thing, and he's in the audience here today. Even. And this is a typical meat for the A-team. Or we can do something else. Of course, we should try to avoid this CO2 release, but we can also do something, because we can reduce the loading and compensate for that. And we have to reduce and reduce and reduce and be a good guy. And there are many ways, when you are in Denmark at least, and also in Holland, but it's more natural to have canals here, but in Denmark it's not natural. But we can try to get the rivers back to the valleys, because then we enhance the self-purification capacity in the system. So that's one way to reduce it. And we really have to think in catchment, not just looking at a lake or a stream or something. We have to go from the one end to the other. Think about reducing input in all kinds of ways, and then do restoration also. And I think we are all doing these water plans now in relation to the Water Framework Directives. And there you have the chance now to change the possibilities of improve the conditions for the systems. And I don't know if we'll do it, but the plan is now to put up 10-meter buffer zones around the streams in Denmark. It will help a lot. It should be 20, but politicians only say 10. And there are other things you can do to improve the conditions. And so we are on the way, you could say, in one way. But I think with lake restoration, we have to think in using multi-methods now. It's not enough to do biomanipulation. We also have to reduce the internal loading and maybe adding aluminum or remove the sediment, because it will be difficult to meet the target in the future. Thank you.
Thank you very much, Erik, for this very inspiring talk, full of data and full of experiences from different parts of the world. And I also appreciate that you not only showed responses of aquatic ecosystems, but also gave us a little bit of a way forward how to solve problems. We are not in a position with the schedule that we can have long discussions after each talk, but still I would like to invite people for a few short questions, and in addition to that, the speakers have declared that they are available during all the breaks for long discussions if you want. So I can allow for a few short questions. Yeah, please.
Yeah, you're saying for food for people, or yeah. I'm not taking this into account, but I think that it's clear that you in the future will have more harvesting of fish. But I also think that, for instance, if you take China, they stock fish in the natural lake systems, and then they harvest them. I think in the future you'll do fish in fish ponds instead of doing it in the lake system. So it'll be much more controlled, where you can control the nutrient input to these systems. So, and you can produce much more fish per unit area if you're using fish ponds instead of using the natural system. And we try to teach the Chinese to shift a little bit there. But it's clear that the need for protein will increase because the population will increase. Yeah, but they also, then you see also that they start to become herbivorous, many of them. If you go from north to south, many of them become herbivorous. It doesn't mean that they are not eating the daphnia also. They like still to get a beef from time to time, but it has the opposite effect, because when they can live on the periphyton, on the plants, on the plant material, then they can have higher stock densities and always be ready to eat a beef if it's coming around. So it puts an even harder pressure on the daphnia than in other systems. But they start eating that, and this is also possible, you could say, because there's a lot of carbon in this, and then the respiration, then you get rid of this carbon, and you can still get the nutrients from this system.
Thank you very much. I'm afraid we have to leave it with this.